Swayam Prabha. Digital India. Educated India.
Welcome to the course on rapid manufacturing. So, additive manufacturing, the process. So, we will try to see here the process chain. So, in the process chain, the first step is virtual CAD model, which we generate using computer. And then after that, we try to obtain the contour information by slicing the CAD model on the computer. This is what we do, and then what we do is we try to make physical. So, making of physical layer due to the contour informations plus we try to merging the physical layers on top of each other. Then finally, what we get is a physical additive manufactured part. Okay. So, this is the process chain. First we do CAD. From CAD, what we do is we try to get the sliced information. When we try to get the sliced information, we also try to get the hatching, and then the information is transferred to a machine. This machine is used to develop from first it develops dot to hatch to layer on top of layer. It finally forms a 3D part. So, as a result, a set of contour virtual slices with even thickness is obtained. Today, this also has changed. You can have varying slice thickness. Machines have been developed wherein which you can have not even, you can also have varying slice thickness. For example, if you have a geometry like this, you can choose up to here as one layer, and then this layer, and then suppose if you have a change in geometry like this. So, the sliced layer can be here, then it can be here, then it can be small such that the change in geometry is accommodated, and then you get. So, this is varying thickness. If there is no change in geometry, you can use a larger thickness. So, that is what is today's technology called as adaptive slicing. Earlier it was slicing of the same thickness. You draw an object, you slice it. The algorithm was like that. Now you have adaptive slicing such that strength, roughness can be optimized and you get the better output. The data set, which is consisting of the contour data, are going to be XY, then the layer thickness DZ, and the layer number of each layer will be there. These are the data sets which will be used while reconstructing the object. Is submitted to a machine that executes 2 elementary process steps per layer in order to create the part. So, that means to say it first moves in XY, then it moves in Z. First, each layer is processed according to the given contour and a layer thickness data. So, this is what we have already discussed, This can be done in many ways by using different physical phenomena. The most simple method is to cut the contour from a prefabricated sheet or foil. So, that is how it is executed layer by layer slicing. In the second step, each layer is bonded to the preceding layer, now forming the top layer of the partly finished mold. Again, the simplest method is to use a contoured foil and glue it on top of the preceding layer. Layer by layer, the physical model is growing from the bottom to the top until the final part is obtained. The basic steps called a process chain are the same for all of the approximately hundreds of different AM machines available today. You take any machine, it will develop only like this. The machines differ only by the way each layer is processed. So, the starting material, if it is liquid, you can use laser. If it is a wire, you can use passing through a hot nozzle. If it is a powder, you can glue that powder, and by the way, adjacent layers are joined to form a part. As a first conclusion, additive manufacturing is the manufacturing process based just on the 3D set, three-dimensional visual objects called as digital product model. This is otherwise called as CAD model. Okay, CAD model. So, digital product model using layers of even thickness contoured according to the corresponding cross section of the product level. So, the conclusion is, in additive manufacturing we always prefer to have even thickness. AM therefore basically is a 2.5D process. Why is it 2.5D? X, Y is 2D and Z will always be small thickness as compared to X and Y. So, that is why it is called as 2.5D process. Okay. The similar thing is also used in CNC machines. We say it is a 2.5 axis CNC machines where X, Y can vary while the process is going on, but Z cannot be varied. So, those processes are called as 2.5D CNC machine, and here in rapid prototyping, since the layer thickness is uniform, it is not changing in the XY plane, it is called as 2.5D process that does not interfere with the design process and therefore can be done at any stage of the product development. That mostly uses proprietary materials, thus forms a strong linkage between machine, process and building material. This proprietary material, today companies have come forward and keeping cost into a predominant effect, they have made it into third party suppliers also. That means to say, company which produces additive manufacturing, for that the raw material can be bought from any customer where the company tries to specify. So, because of that opening it out, there is a competition between these companies. So, material cost has come down drastically. So, proprietary materials which was earlier, now slowly this is also getting changed. I am walking you through the academic what is available in a book and the latest research what is going on. So, when I said varying thickness, please understand that is still in the research state, and there are few companies which have started claiming that in their products they do varying thickness, and that too varying thickness not in one layer. In one layer they can't change the thickness, between layers they can change, and in the same way proprietary materials, now it has been opened out for third party supplier. This effect will diminish with increasing number of machines in the market and the rising attraction of third party material suppliers enter into the market. So, this is what I was trying to tell you. Most of the people's interest in additive manufacturing preferably wanted to know how they can use this new technology and what kind of new and different products they can develop using it. This is what people always will try to think of. I have a machine, what I can do from that machine. So, for example, people make wonderful carving out craft from the existing lathe machine. So, the creativity when it is added to the machining operation, it tries to come up with new products. So today people are looking at additive manufacturing and then they are looking at what can it do, what new things it can do, what all different products I can develop. In addition, it's advantageous to use the right term during the discussion in the product development team. Many things that each of the different AM processes is exclusively linked to a certain application, in the sense that a certain AM process can only be used for one or a small range of application, while the other processes is solely suitable for another application. So this is a thinking which people had, but today what is happening is slowly this is also getting removed out. Today we have polymer material, which is a starting material for additive manufacturing. It has blended polymer, it has impregnated polymer. So impregnated, it has metal impregnation in a polymer. So many things are coming up today. So earlier it was said, for this particular application please use this process, but today slowly that is also getting moved out. Additive manufacturing, that rapid prototyping, is now getting more and more generalized. This opinion encourages people to study all different processes first and to care about a suitable application afterwards. In practice, identification of the best applicable AM process starts with the respective application. So that is what it goes. For example, if you wanted to have a spoon to be made, okay, a spoon to be made, you should first understand what are all its mechanical forces which are getting acted. Then you try to see its usage, then you try to see its economy, and then you decide which additive manufacturing process to choose. So for every product we have to choose a proper cost effective performance based additive manufacturing process. Then special requirements such as dimension, resolution, surface quality, tolerances, temperature, etc. lead to the suitability of the material. For example, once you start working on powder based materials, your resolution of the part you get is very high, the tolerances are very tight. If you use wire, you might not get the same tolerance. And second thing, tolerance is also directly proportional to the wire, whatever raw material form and dimensions or shape. So the special requirements such as dimension, resolution, surface quality, tolerable mechanical force, temperature, etc. lead to a suitable material, and finally to a machine capable of handling all these requirements properly. In general, different additive manufacturing process can use alternative to solve the same problem. So what we are trying to say is, you have AM1, you have AM2, you have AM3 machines or processes. So all the three processes can lead to one output product. Okay. To define such a structure, first the meaning of the term technology has to be distinguished from application. As technology is defined as a science of technical process and describes the scientific approach, application means how to use the technology to benefit from it, which is also called the practical approach. So this is the definition for technology. To obtain a better overview, different classes of application, so called application levels, are defined to apply this technology. The definition are widely accepted but not standardized yet, and despite all standardization efforts, sometimes there is always a different terms in usage. So AM technology is characterized by two main application levels. One is rapid prototyping, the other one is rapid manufacturing. As can be seen in the illustration, AM technology is characterized by two main application levels, rapid prototyping and rapid manufacturing. Rapid prototyping describes all applications that lead to prototypes, samples, models, mock-ups, while rapid manufacturing is used when final parts or even products are made. So, AM technology level and the two application levels. So, let me draw the same schematic diagram which we used earlier. Now, we will try to have a deeper insight. So, this is going to be additive manufacturing. The next one is going to be rapid prototyping. Rapid manufacturing. So, here we have prototyping, here we have manufacturing. This is technology. So, this schematic diagram is given by Gebhardt. From the book Understanding okay. So, this we saw earlier. So, this is additive manufacturing, which is a technology, then rapid prototyping, rapid manufacturing. This is the manufacturing which is there in levels. Regarding the application level, rapid prototyping has two sub levels which can be distinguished. One is solid imaging and concept modeling on the one hand and functional prototype on the other hand. So, solid imaging and concept modeling on one hand and functional prototyping on the other hand. Solid imaging or concept modeling defines a family of parts that are applied to verify a basic concept. Please understand, solid imaging or concept modeling defines a family of parts that are applied to verify a basic concept. The parts resemble a three-dimensional picture or a statue. In most cases, they cannot be loaded. So, because it is not the original part, it is not the original part, not original part. It is only for prototyping. So, this has to be OR. They are used just to get a spatial impression in order to judge the general appearance and the proportions. Because of this, the parts are also called as show and tell models. So, please understand, this is solid imaging, concept modeling and show and tell models, all are almost the same. So, it cannot be used for any functional application. So, AM application level, rapid prototyping, sub levels solid imaging and concept modeling. So, here if you see that the same image whatever we have discussed earlier, which is nothing but additive manufacturing, rapid prototyping and rapid manufacturing, you have here, this is what is a level which is called as solid imaging concept modeling. So, we are just taking an example of a process which is very much popular in rapid prototyping, which is called as stereolithography. Initially, it was very popular, then slowly because of its cost per part is so expensive, this technology is overtaken by many other technologies. But today once again stereolithography has come into action when you want to make miniaturized and very small parts. So, stereolithography is an additive manufacturing process which employs a vat. So, this is a vat. So, the entire box which is there, that is called as the vat, is which employs vat of liquid ultraviolet curable photopolymer. This is the polymer which is placed. This polymer is placed in a tank which is called as vat. With the polymer is otherwise called as resin, and a UV laser is used to build the part layer by layer, one at a time. Liquid photopolymer is nothing but UV curable photopolymer, and then what I use is I use a laser which is UV. What is UV? Anything less from 150 nanometer to somewhere close to 300 nanometer. Okay. So, this is UV. So, we use this UV laser to hit at a galvo. This is called as a galvo mirror. So, the advantage of this galvo mirror is you are not mechanically moving any part. This galvo, what it does is it just sweeps and tries to take the information from the laser, and it starts curing layer by layer. And once one layer is done, this table either can shrink down or can go down, not shrink, it can go down, or the laser can go up. Generally what happens, the vat tries to move down. Okay. Once one layer of information is there, one layer of information, everything is getting transferred from the laser through the lens to the galvo mirror, and from the galvo mirror it is hit at a surface and it is cured. So, here first it is done spot, then it is done a raster, then it is done a layer. Okay. So, here is a sweeper. So, what happens is once the vat sinks down by a layer, in order to maintain uniform thickness, excess resin is removed by using this sweeper. So, this is the part which is already made because of UV curing, and this is the platform on which the part is getting built. Okay. And why by looking at the wavelength itself, you can decide that the resolutions are very good. Resolution is directly proportional to the wavelength. So, if the wavelength is small, so the resolution of the feature whatever is getting built is high, and on top of it you have these lenses to modify the beam quality or the beam shape, whatever it is. Okay. So, this is a typical or a simple example of rapid prototyping technique. So, whatever the part has come out here, it is only a show and tell part or a concept part which is used to give a customer a feel that this is how it looks like, or they can check the proportionality, or they can check the form and the fit. So, the scaled concept model are often used to verify complex CAD drawings. Here they are called as data controlled models, as well we will see it in the next figure. Data control models. Data control does not only mean verifying the CAD data, but to provide a basis for interdisciplinary discussions as they occur. Example, in packaging problems. In the case of convertible roof assembly model shown in the figure in the next slide, it helps to balance the idea from divisions specialized on different aspects of the soft top and the electric mechanism and the kinematics. So, this is a concept model scaled assembly of a roof construction of a convertible passenger car. Okay. So, it is done by laser sintering and polyamide 2 is used as the material. The colored models made by powder bind process of 3D printing are valuable tools for concept evaluation. For example, if you are trying to give a topological information about a space, so you would like to show the mountain as brown in color, water blue in color and the green pasture as green and constructed buildings of some color. So, here in rapid prototyping you have this advantage, you can also blend colors while developing the printing or while developing the part. The coloring helps to indicate the problematic area of the product and to structure the discussion. Figure in the next slide shows a solid image of a cutaway model of a combustion engine unit. In reality, the parts are not colored. The different color of the model can be linked to the topics of the agenda. So, you look at here, we have made parts of different colors, so that it is very visible and you can also try to see where the problem lies. The example what I gave for topological information, so that is also possible. So, people try to draw terrains, okay, and then they used to get. So, we also try to add colors while printing. So, cutaway demonstrating parts of the combustion engine unit which is 3D printed is shown here. This the machine which was developed was Z Corporation. So, here what they do is they try to use powder and they try to use resin. In that resin they try to mix colors. So, that is how you get the color. So, what is functional prototyping? It is applied to allow checking and verifying one or more isolated functions of the later product or to make the production decision even though the model cannot be used as a final part. So, here what we do is we try to look at only functional aspects. Earlier we were trying to look at form, fit and other things. Here we would also try to look at slightly more than that. Actually, when we talk about fits, functional prototype is also used for looking at fits. Okay. As can be seen in the figure below, the adjustable air outlet grill for the climate adjustment nozzle of a passenger car can be used to verify the air distribution in a very early stage of the product development. It was made in one piece using laser stereolithography. So, laser stereolithography was the process which we discussed till now, and 3D Systems is a company which develops this. So, this is a filter, this is an adjustable nozzle head and then this can sweep and try to mix the air inside a car. So, when we talk about functional prototyping, going back to the same figure, this is additive manufacturing, which is rapid prototyping, rapid manufacturing. We saw here earlier it was solid imaging and concept modeling. We have a next thing which is more towards functional prototyping. So, test form, fit, function with models built in tough ABS plastics for functional prototype is shown here. This is a shock absorber which is used for automobile application. So, now let us move to the next part which is on rapid manufacturing. The application level rapid manufacturing summarizes all processes that deliver final products or final parts that need to be assembled to become a product. An AM part is called a product or a final part if it shows all characteristics and functions that are allocated to it during the product development process. Okay. So, during the product development process, if you can add characteristics and the function that are allocated to it during the product development process, it can be done. If the resulting part is positive, the process is called as direct manufacturing. If it is negative, which means a die, a mold or a gauge, it is called as direct tooling. Please understand the difference between these two. The negative of direct manufacturing becomes tooling and the positive becomes rapid manufacturing. Direct manufacturing leads to final parts that directly come out of AM process. Today we are looking at rapid prototyping getting converted into rapid manufacturing and producing the parts in the mass customized way what we want. So, rapid manufacturing today a broad variety of materials from all material class, plastic, metal, ceramic are available to to be processed directly using AM process. Here it is not important that the available materials show exactly the same physical properties as the materials used within traditional fabrication process. However, it must be assured that the properties on which the engineering design was based can be realized with the chosen AM process and material. The figure shows here cobalt chromium alloys have been used for selective laser melting. So, in rapid manufacturing, the data was obtained from the patient by a dental imprint and then digitized. With the use of the professional dental software 3Shape, the dental bridge was designed and directly manufactured using a SLM process, selective laser melting process of chromium cobalt alloys. After finishing and geometric testing, the bridge was ready to be placed in the patient's mouth. So, this is direct manufacturing 3-unit dental bridge.